Thank you very much. Thank you to the organizers for the invitation. I would like to talk about some results obtained in collaboration with Doreen Bukur, mainly containing these two papers, concerning the use of free discontinuity techniques in order to address some issues coming from shape optimization, especially under the Robin boundary conditions. And to focus on a classical problem, I will mainly concentrate on the problem of the first eigenvalue of the Laplacian and variants of it. So the first eigenvalue of the Laplacian under the Robin boundary condition is defined in the usual way. The Robin boundary condition at the involves the normal derivative and the trace of u at the boundary, and the constant beta, which appears, is strictly positive. So we need some regularity for the boundary in order to settle this condition. And formally, the Robin boundary condition is somehow intermediate between the Dirichlet condition and the Neumann condition. Also formally, we obtained the Neumann condition by setting beta equal to 0. And we obtained Dirichlet by setting formally beta equal to plus infinity in order for u to be constrained to be 0. And the first eigenvalue is defined as as usual as the lowest lambda for which this problem has a non-trivial solution. And the first eigenvalue under Robin condition has some features which are very similar to Dirichlet. For example, the first eigenvalue is simple. The associated eigenfunction has a definite sign. Indeed, in the case of Robin, as we will see in a moment, the eigenfunction can be chosen to be positive, but indeed strictly positive on the closure of the domain. But other features of the eigenvalue are completely different. For example, what is missing is a simple rescaling formula under dilations for the eigenvalue under Robin conditions, which is particularly useful in the case of Dirichlet. And moreover, what is missing is the monotonicity under inclusion. So in the case of Robin, it's no more true that if you have a domain which contains another domain, the eigenvalue of the larger domain is below the eigenvalue of the initial domain. So if we try to minimize the first eigenvalue on the class of, for example, Lipschitz domains under a volume constraint, we go to the ball. And this is the Faber-Kran inequality, which holds true also for the case of Robin conditions. The inequality was conjectured by Polya in the 50s, but a complete proof is surprisingly recent because it's due to Danners in 2007, who generalized to n dimensions some arguments contained in a paper by Bossel dealing with the two-dimensional situation. So among all domains sufficiently smooth, Lipschitz, then the ball minimizes the eigenvalue, and moreover the equality holds if and only if the domain is the ball. In order to underline some differences with respect to the Dirichlet case and also to prepare the way for the free discontinuity approach, let me spend briefly a couple of words about the proof in the Dirichlet case. So the proof in the Dirichlet case is not variational. It's a direct comparison between the domain and the ball with the same volume, and it's done by now the standard proof is by rearrangement, symmetric decreasing rearrangement. So the starting point is the representation of the eigenvalue under Dirichlet condition as the minimum of a Rayleigh quotient. Then one takes the first eigenfunction on the domain omega, and one takes a symmetric decreasing rearrangement of this function to get a function u star on the ball with the same volume centered at the origin. So this new function u star preserves the regularity, so it is W12 and vanishes at the boundary. Then this new function is equimeasurable with respect to u. So in particular, every LP norm is preserved. Here, the L2 norm is what is important. And one checks that the gradient, the energy of the gradient decreases under this operation. So now, since U star is admissible for the computation of the eigenvalue of the ball, then we get this first inequality. Then, since the denominator is preserved and the energy of the gradient decreases, we get the second inequality. But this Rayleigh quotient is nothing but the eigenvalue of our initial domain. And so we see that the eigenvalue under the Dirichlet condition is larger than the corresponding eigenvalue for the ball of the same volume. And if this chain of inequalities turns out to be a chain of equality, then omega is seen to be equivalent to a ball. Then this method of proof is very stable, because we can pass immediately to some sort of semilinear variance of this eigenvalue by replacing the u square at the denominator with, for example, u to the power q. Then we raise everything to the power 2 over q to preserve the homogeneity of the Rayleigh quotient. Then, as long as q is subcritical, so below the critical Sobolev exponent 2n over n minus 2, then a minimizer exists. And the very same proof that we saw before shows that, again, the ball is an optimal domain under the volume constraint for this kind of variance of the linear eigenvalue. And in, for example, the case q equal to 1 has a particular name. It is called the torsional rigidity. And it is a coefficient which comes into play in the theory of, in the elasticity theory of beams. And in particular, the optimality of the circle in 2 dimensions was conjectured by Saint-Venant in the middle of the 19th century. And then it was proved much later. If we move to Robin, then the situation is very different, because we still have a representation of the eigenvalue as the minimum of a Rayleigh quotient, but now we have an extra term, which of course keeps track of the Robin boundary condition. This extra term is a trace term, so it takes into account the value of u at the boundary. And this term scales in a way completely different with respect to the other two guys. So in particular, this is why we don't have a simple formula for the eigenvalue under dilation. And moreover, since the admissible functions for the computation of this Rayleigh quotient do not vanish at the boundary, and indeed the value at the boundary is important for computing the Rayleigh quotient, we see that we cannot use rearrangements, because we are not sure that the energy of the gradient under rearrangement decreases. And moreover, we don't have a good control on surface terms, trace terms under rearrangements. So indeed, very simple one-dimensional examples show that if you perform a rearrangement, then the value of the Rayleigh quotient in the symmetrized configuration is higher with respect to the original situation. So this means that in order to prove the Faber-Krahn inequality in the case of the linear eigenvalue, we have to follow a completely different kind of approach. And the Bossel and Danner's approach is again based on a direct approach, a direct comparison between a domain and the ball. Well, the technique is somehow, it's not easy to describe. Essentially, the starting point is a good representation formula for the eigenvalue on omega through some integral expression which they call the H functional, involving the first eigenfunction on the domain omega. And now what they do is essentially precisely the opposite that we do of what one does in the context of Dirichlet. So one takes the first eigenfunction on the ball and move it back to omega. And using this representation, one shows that the ball is optimal and that uniqueness holds only if omega is precisely the ball. So this kind of technique is particularly is tailored precisely to the case of the linear eigenvalue. That is, that this representation through the H functional completely fails if we move to, by analogy, we move to some sort of semi-linear variance of the eigenvalue as before by replacing u squared with u to the power q. Then the representation through the h functional does not work. And so formally one can ask again, for every q subcritical, is or not the ball the minimizer of this sort of principal frequency under a volume constraint. Okay, except for q equal to 2, that an interesting case, of course, there was no idea. Well, in the case q equal to 1, that is the analog with Robin condition of the torsional rigidity, which is just a formal analog because the interpretation in terms of elasticity requires the function to vanish at the boundary. So it is just formally a torsional rigidity with the new boundary conditions. Well, it was proved by Bandel and Wagner that the ball is a good candidate for optimality, at least in a local sense. They computed a sort of shape derivative of the torsional rigidity at the ball with volume preserving deformation in the first approximation. What they proved is that the first derivative vanishes, while the second is strictly positive. So we have essentially a sort of at least a local minimizer, perhaps. Okay, so together with Doreen, we tried to deal with the problem with a completely different kind of approach using free discontinuity techniques. And for example, one of the results that we obtain is that under a certain range for the parameter q, for example, for q between 1 and 2, and I will comment on this restriction later on, then we have that indeed the ball is the minimizer of this generalized eigenvalue under a volume constraint. And indeed that the equality among Lipschitz domain, for example, holds if and only if omega is precisely the ball. So in particular, we reobtain the classical case, q equal to 2, but we fix also the case of the torsional rigidity, and indeed by the same technique, we cover all the intermediate cases. So our approach is completely variational, and I can describe the approach as composed of 2 steps. Well, the first step is to guess a good class for admissible domains containing the regular ones, and for which we can find a minimizer of the generalized eigenvalue under a volume constraint. Of course, since we have to enlarge the class, we have to properly redefine or extend the definition of the principal frequency to the new domains. This is the hard part of the analysis. The second part is, in comparison, is relatively easy because one can show that if an optimal domain exists, then simply by some geometrical consideration like symmetrization, integration by parts, one shows that indeed optimal domains are equivalent to balls. If the first part is indeed quite hard from a technical point of view, because it involves the ideas from free discontinuity problems, and of course it's much more technical with respect to the Danner's approach. The advantage is that, okay, on one hand we can fix other cases like the torsional rigidity. This is somehow a little bit technical, of course, because the relevant case is the case q equal to 2. The point is that this class turns out to be a good class in order to a good framework also for different shape optimization problems. So different from the problems like eigenvalues or variants of eigenvalues. Okay, so let me describe the first part essentially of this approach. Well, the first step in order to guess a good relaxation, so a good new framework for domains, should be to see if we have some compactness for the domains when we try to minimize the eigenvalue. And okay, there is no trivial compactness for the domains, because if we take, for example, a minimizing sequence with a fixed volume, then one can say, okay, one idea could be, let's try to bound the perimeter, since the first eigenfunction is strictly bounded from below by a positive constant. This is not a good idea. Well, okay, it's a good idea, but it's not very efficient, because in the Rayleigh quotient, the boundary is involved also in connection, of course, with the trace of the eigenfunction. And what is missing is some sort of uniform bound from below for the eigenfunctions along a minimizing sequence. So there's, at least it's not so evident that we can get some trivial compactness, like bounding the perimeter, trying to get some L1 lock compactness for a minimizing sequence of domains. So from the point of view of the domains, no clear compactness. The situation is completely different if we look at the eigenfunctions. And precisely if we try to see the eigenfunctions as functions defined on the whole space, but with some discontinuities at the boundary. Well, the idea is to take the first eigenfunction and to extend it to 0 outside the domain. Let's take the domain to be fairly smooth, okay? And then we extend by 0. The new function, of course, has some discontinuities at the boundary, because the eigenfunction is strictly positive on omega bar. What turns out is that it's quite easy to bound the BV norm of U square, this new function on the entire Rn. And the computation is very, very easy, because if we want to compute the BV norm of U square, then we have, okay, the L1 norm of this function, but the function is 0 outside the domain. So we have, sorry, here I wrote everything on the entire space. So we have the L1 norm of the function, U square on Rn, and then we have to bound the gradient. Well, the gradient by the chain rule has an absolutely continuous part, which is 2u nabla u. And then we have the contribution of the discontinuity, which in this particular situation, the jump set j of u is just the boundary. And so what we have computed is the jump of the function. So we have a trace from inside, which is u plus square, and a trace from outside, which is u minus. But here the situation is particularly simple, because the function is smooth inside and 0 outside. So what we have is that, okay, the last term we can simply integrate on omega. Then the first term is again integrated only on omega, because outside u is equal to 0. So we have 2u nabla u on omega in modulus, which we estimate by u square plus nabla u square. So we have the first two terms. Then we have the jump term. One of the two traces is 0, u minus. The other one is simply the trace, u square. And so we recover this term, which is the trace term in the Rayleigh quotient. So if we put integral of u square in front of everything, what we get is that there is a bound in terms of the first eigenvalue under Robin condition, with beta appearing and two constants depend on beta, of course. And since usually u square is normalized to 1, then we see that if we bound the classical eigenvalue, what we bound quite easily is the BV norm of this extended function, u square. And the same kind of computation can be done if we pass from 2 to another parameter q in the denominator to get this semilinear variance. And so again, what we bound along a minimizing sequence is the BV norm of u square. So this simple computation shows that while from the point of view of the domains we don't have a clear compactness, some compactness is available for the functions. So one idea could be that of reinterpreting the Rayleigh quotient as a free discontinuity functional. Why not? A good reinterpretation is the following. So we keep the structure of the Rayleigh quotient, and we replace the surface term by a discontinuity term, so a sort of a jump energy. So we integrate on the jump set of u the sum of the two traces, u plus and u minus, from both sides of the jump set. If we start from a regular domain omega and we extend by 0 as before, we immediately check that the free discontinuity functional reduces precisely to the Rayleigh quotient, because the integration are only on omega, and one of the two traces is 0, and the other trace is simply the trace in the sense of Sobolev spaces on the boundary. But then, of course, if we restrict our attention to regular domains, several forms for the jump energy could be good, because one of the two traces is 0. While here I chose to write the sum of the energy square, u plus square plus u minus square. Why the sum? Well, the sum is the correct form of the energy for this kind of problems. It's a little bit unusual for free discontinuity functional to have this contribution in terms of sum of the traces. For example, in the applications to continuum mechanics, so for example, in cohesive fracture, it's more natural to have the difference of the traces to some power, because the energy paid by the opening of the fracture, of the crack, depends essentially on how far the two lips are one from the other. So essentially the difference plays a role. While here, it's more natural to have the sum. And one understands this point by looking to a situation of this type, when we have a domain with a hole, which we assume, I don't know, to be minimal, okay, then in the limit, why not, the hole can shrink to a crack. If it shrinks to a crack, then the eigenfunctions, if they converge, they should converge to something on the new domain omega with a crack, and there's no reason for the two traces of the limit of the eigenfunction to be equal. So in principle, they can be different. And moreover, the contribution of the two lips of the holes precisely contribute in the limit by the sum, okay? Because we have the contribution from above, which gives the u plus square, and the contribution from below, which gives u minus square, but with the sum, not with the difference, okay? So this is the main motivation for this unusual surface term in the free discontinuity functional. So the previous consideration at least suggests that a good problem to look with to get an insight into the problem on the original problem on the domains could be that of trying to minimize these free discontinuity functionals on functions for which we have somehow some compactness. And the compactness that we saw before involves the u square, the BV norm of u square. So a good candidate to try to look for minimizers could be this class of functions. So functions which are in L2, greater or equal than 0, because eigenfunctions can be chosen to be positive. So this is not a restriction. Then we should have a BV norm on u square, since here what matters are the discontinuities, the jump discontinuities. We can restrict to the class of the so-called spatial functions of bounded variations, SBV. So these are functions which are in BV, for which the gradient in the sense of distribution is a measure. The measure has two parts. The first one is absolutely continuous with respect to the Lebesgue, what we indicated with the nabla u. And the second part, the singular part of the measure, is concentrated on a discontinuity set. So what is missing is the so-called Cantor part of the derivative, for example, of the Cantor-Vitali function in one dimension. So here is the SBV function. And then we keep the volume constraint. Here the volume constraint is rephrased in terms of the volume of the support. So a good problem, well, a related problem, could be that of minimizing the free discontinuity functional on this class of functions. And what is the intuition? The intuition should be that if we have a minimizer for this free discontinuity functional, probably by looking at its support, we can guess what could be a good class for domains in order to settle the problem of the original problem of the minimization of the eigenvalue. Of course, this is subordinated to some regularity issues for the minimizer, because in general SBV functions can be very complicated. So in principle, the support can be only a Borel set, which is a little bit too far from a good notion of domain, at least because, okay, one could hope, one should require at least to be open. But moreover here, since the Robin conditions play a role, we need also a boundary with the normal in some sense. Otherwise, we are too far from a Robin condition. Okay, if you don't know precisely what SBV is, you can think of SBV as piecewise smooth functions with some discontinuities along some hypersurfaces in the space, which we call the jump set J of U. Along these hypersurfaces, we have two traces from one side and the other side, U plus and U minus. We take U plus square plus U minus square, and we recover the surface term in the energy. Of course, SBV functions are much more complicated than this. For example, J of U can be dense in the space, and this is clearly a source of difficulty for the problem. And another difficulty is that indeed it's U square which is assumed to be SBV, because the natural bound is on the square of the eigenfunction. So this is another source of difficulty, because indeed one can find very simple one-dimensional examples in which U square has bounded variation but U has not. And the problem is when the values of the function accumulate near zero. Otherwise, one can use the composition with the square root, the standard chain rule, to get the SBV regularity. Okay, so let's try to see what kind of regularity we can find for the minimizer of the free discontinuity function. So the first point is to prove that a minimizer exists. And here, what we can do is that indeed a minimizer exists as long as Q is between 1 and this 2n over n minus 1, which is somehow natural as an exponent because U square is BV. So it's by immersion is in ln over n minus 1. So U itself is in 2n, L2n over n minus 1. So this is an exponent which is strictly below the Sobolev exponent. But it is somehow natural for this kind of approach, since U square has a summability which is naturally n over n minus 1. And moreover, there is another interesting point, that is that as long as Q is below this exponent, what one can show is that even if there is no simple formula for the eigenvalue under dilation, what can be shown is that if we dilate our domain, then the eigenvalue decreases. And this is used several times in the analysis. So if we enlarge the domain by a homotety, then the eigenvalue decreases, even if there is no a good formula for dilations, and even if in general the monotonicity is lost for Robin. So the first point is, okay, there exist minimizers. This is not completely trivial because the problem is we have some compactness, but the problem is invariant under translation. And so we need some concentration compactness argument in order to prove that indeed the minimizer exists, in order to reduce to a compact case in which we can use the compactness even by the bound of the BV norm of U square. Okay. Then what about the properties of the minimizers? Well, what one can prove is, firstly, which is very important, is that the minimizers are bounded from above and below. So the minimizers are L infinity, and moreover, one can prove that there exists a constant which is strictly positive, such that u is greater or equal than this alpha almost everywhere on the support. So the picture is that we have this bounded function which immediately jumps to 0 outside the domain with a definite amount of jump when passing from the support to the complement of the support, of course, almost everywhere. So these two properties are precisely the analog in this weak setting of classical properties of the eigenfunctions. So the eigenfunctions are, one can prove easily that they are bounded in L infinity. They are smooth inside if the domain is smooth. And also the bound from below by a strictly positive constant is the outcome of the interplay between the Hopf principle and the Robin boundary condition in a smooth case. So if omega is smooth and we concentrate on the classical eigenvalue, then one can say, okay, the first eigenfunction, which we take positive, is superharmonic, so it has a minimum point at the boundary, which we call x0. But at that point, by the Hopf principle, the normal derivative is strictly negative. Then we use the Robin boundary condition, that the normal derivative plus beta u is equal to 0 at the boundary, and so we infer that beta u at x0 is strictly positive, which means that indeed the first eigenfunction is positive on omega bar, not only on omega. So this result, so the second property, is somehow the analog of this property, but in a weak setting. Of course, the proof should follow completely different arguments. And indeed, it is based on some ideas by Bukur and Lukaus, which then we revisited using somehow a sort of de Giorgi iteration technique in the second paper I quoted at the beginning. So this is a very technical point, but it is crucial for what we are going to do now, because let's see some consequences of the bound from below. Well, the first consequence is that, okay, the surface energy is u plus square plus u minus square. So this means that on a jump point, we have that this u plus square plus u minus square is bounded from above and from below. And so what we get is that, for example, the surface of the jump set is finite, which is not clear at the beginning because the dependence on the trace could, in principle, permit functions to accumulate near 0 and having a huge amount of surface for the discontinuity set. This is not the case. The surface of the jump set is finite. Moreover, what we get? We get also this chain of inequalities. That is that, let's assume to normalize the minimizer in LQ. Then the Rayleigh quotient, the free discontinuity functional, reduces just to the variant of the energy which involves only the gradient u square and the jump term. Now the jump term is bounded from above and below. From below it is bounded by the constant beta alpha square, and from above it's bounded by 2 beta the L infinity norm of u, because we know that u it's in L infinity. So this means that the free discontinuity functional on the minimizer is bounded from above and below by 2 Mumford-Shah energies, but with 2 different constants, beta alpha square from below and the other constant from above. So we have this picture of a strange free discontinuity functional, which is somehow natural from the point of view of the minimization of the Robin condition, with a strange surface term, for which we have that the energy is bounded from above and below by the 2 Mumford-Shah energies. And indeed, in order to get, in order to be fair, in order to get these inequalities, it's crucial the bound from below, and to prove the bound from below, the fact that we have to compute the sum of u plus square plus u minus square plays a role. So it's a dependence on the trace, but the fact that the sum is involved is crucial to get this inequality. And this inequality is not just a numerical inequality that we check. It's also a kind of inequality which is stable in the sense that we can recover some minimality properties involving these two Mumford-Shah functionals for the minimizer U. Because what we get is this notion, is this property of quasi-minimality. So if we change U inside a little ball of radius r, we change U to V, then what we prove is that the first Mumford-Shah energy for U in the ball is less or equal than the second Mumford-Shah energy for the new function V plus an error term, which is of a volume type, which is C times the radius to the power n. And so we have an inequality which looks pretty much the inequality considered by the Giorgi, Carriero, Leaci in their famous paper on the regularity of the Mumford-Shah functional. Here the difference is that it's natural that we get two different constants. But if one looks at the proof of the Giorgi, Carriero, and Leaci, one realizes that indeed the fact that here we have two different constants is not so important. One has to readapt certain steps, but essentially their proof can be adapted to get information also for this kind of local minimality. And the conclusion is the same. That is that the conclusion is that the jump set is topologically regular. So it's an essentially closed set. If we take the closure, then the set is not increased too much because the Hn minus 1 norm of the closure of Ju minus Ju is equal to 0. So Ju can be considered as a closed set. So the picture that I alluded before with the function with a dense jump set cannot occur for minimizers of this free discontinuity function. So J of U is a closed set. And this is a very good property in order to infer some regularity for the support, because our initial target was to get informations for the new class of domains by looking at the supports of the minimizer. Since Ju is essentially closed now, the support of the minimizer is pretty regular, because the idea is that how can we get the support? We take the jump set, which is closed. We can assume it to be closed. We take the complement. We select the connected components on which U is not 0. Indeed, it is bounded from below by a strictly positive constant. That is the support. So it's an open set with a boundary which is somehow regular because it's given by the closure of the jump set of U, which we know by the general theory to be, for example, a rectifiable set, for which we can define point at Hn minus 1 almost every point. We can define a normal, which is important for the Robin conditions. So let me summarize some properties that we have for the support of the minimizer and for the minimizer itself in terms of its regularity. So we have that the support is an open set. The boundary is given by the closure of the jump set. Well, inside, since the function is a Sobolev on an open set, is strictly bounded from below, then we can play with the functional to get the Euler-Lagrange equation. So what we get is if Q equal to 2, it's the Eigenvalue equation. And so we get that the function is fairly smooth inside. It's smooth, but it is also analytic inside in view of the equation, because it is bounded by a strictly positive constant from below. Moreover, one important point is that by optimality, omega is connected. It cannot be disconnected because it would be easy to prove that if it has two connected components, one of the two with U restricted on that part would provide a value for the free discontinuity functional which is strictly better than the minimum.
But this is usually based on some homogeneity property of the function, right?
Well, here you can play also with some trivial inequalities like, I don't know, the minimum if you split if you split the Rayleigh quotient in the two parts, you have some sort of a plus b over c plus d. And then you play with the fact that the minimum of a over c, b over d is less or equal than this. And so one of the two is optimal. Okay.
You still don't have this, you don't have the scaling properties.
You don't have the scaling properties. Here you have the scaling property in the sense that if you take one of the two, then you are losing the volume constraint, and you have to rescale by a homotety. But under a homotety, the eigenvalue decreases. So you get a strictly better, yeah. It's not the homogeneity formula which is missing, but it is the fact that it is decreasing under dilations. Okay. Okay.
Of course you have this extension trick that allows you to do this kind of thing.
Yeah, of course, of course.
Which
Of course.
you can have, now I start to understand.
Okay, so what is a good framework? So which is what is the framework suggested by this kind of approach? Well, the framework could be this. Well, let's concentrate on open sets with a finite volume and with the topological boundary, which is rectifiable with a finite surface, which is, this is precisely the case of the support of the minimizers. And then what could be a definition for the eigenvalue in this new setting? A definition could be obtained by mimicking a little bit the free discontinuity functional. That is, let's take a function u, which is a Sobolev inside L infinity, to be sure that when we extend to 0, we get some BV function on the entire domain, so that we can define safely what is u plus and u minus at hn minus 1 every point. Then we integrate on the boundary of u plus square plus u minus square. It can happen that the two are equals. Okay, in this case, why not? Then we take the infimum. Of course, in the case of a regular domain, this definition reduces to the classical definition. And so what one can check is that indeed this class is a good class. So if we look for minimizers of the first of this eigenvalue in this class, we have the existence of a minimizer, and the minimizer is precisely the support of a minimizer of the free discontinuity functional. So we can easily check in view of all the analysis involved for the free discontinuity functional that indeed the minimum problem on this class of domains indeed has a solution, and the solution is a domain which is connected, which is important. The function inside is positive, super smooth because it's analytic. And what we have is also that since the minimizers are precisely the supports of minimizers of the free discontinuity functional, we have that if we have the associated eigenfunction and we extend it to 0, what we have is that the boundary of u of omega is precisely the closure of the jump set of this extension. And this is important. Okay, so what are some important properties of this new class of domains suggested by the regularity analysis? Well, first of all, we have that this class, a domain can be, we can have essentially some external boundary. Of course, what we have is that also cracks inside are admissible, okay, because the topological boundary should be a rectifiable set. And indeed, jump discontinuities played a role in the previous analysis. So a general picture could be like this. We have some weak regularity in the sense of geometric measure theory for the boundary. We have an external boundary, which is the reduced boundary of our domain. But then we have also some extra terms, which could be cracks inside, some sort of inner boundaries. Of course, this class is quite stable, for example, by intersection, by reflection across hyperplanes. And at least we have that open sets inside this class have a finite perimeter. So at least we can employ some integration by parts on the reduced part of the boundary, which can be important for the Robin boundary conditions. Okay, now in the time I have 50 minutes. Okay. Let me show you why under certain assumptions, under certain restrictions for Q, it's easy to see that optimal domains are balls. So the restriction is that Q is between 1 and 2, and there is only one point in which I use this restriction, which is the first one, because the strategy is this. In the first step, one proves that the eigenfunction of the domain is a radial function with respect to a suitable origin. So the function enjoys some circular symmetry. In this place, I use the restriction Q between 1 and 2. Then, in a second step, one shows that since the function is radial, also the domain should have some circular symmetry. And one can prove that it is either a ball or an annulus. Then in the end, one checks that the eigenvalue of the ball is better than the eigenvalue of the annulus, and one has the optimality of the ball and the Faber-Kran inequality. So let me show you the first step. But the first step is based on this numerical inequality, which is true for Q between 1 and 2, and it is false for Q larger than 2. And this is the only place where we use. Then we use this inequality plus the Euler-Lagrange equation, which says that the function u is analytic inside, and we use the fact that omega by optimality has to be connected. And the idea to show that u is radial is to use reflection arguments. So the idea is, okay, let's fix a hyperplane orthogonal to the first axis. We move it until we split the domain in two parts with the same volume. Then we perform a reflection. There could be cracks inside, okay, which are not in the picture, but can be admissible for the geometry of the domain. Then we have that by symmetry, we can create two symmetrical domains, symmetrical with respect to this hyperplane. Then, in view of this inequality, okay, we have that one of the two pieces is optimal again, because what we have between brackets is precisely formally the energy that we obtain by reflection. And so one of the two pieces is again an optimal domain. So we have a new optimal domain. The associated eigenfunction should be the reflection of our original eigenfunction through the hyperplane. Then we take an hyperplane orthogonal to the second coordinate axis, and we play the same game on the new domain. So we get a new domain, which is again symmetric also with respect to the new hyperplane, but the symmetry with respect to the first one is preserved in view of the orthogonality. Then we proceed in this way until we obtain a domain which is symmetric with respect to n planes orthogonal to each other, which meet at a point which we take as the origin of our new system. Then this new domain is optimal, and so it is connected. Now we prove that the associated eigenfunction of V star, which is given by some successive reflections of our original eigenfunction, is a radial function, and we prove it in this way. We prove that the tangential derivatives are 0. This suffices to conclude because the function u is analytic. So if tangential derivatives are at every place equal to 0, then since the function is analytic and the domain omega star is connected, then we get that the function depends only on the distance between the point and the origin. And again, the tangential derivatives are 0 by reflection argument, because we take a point x and we take a tangential direction with respect to the line which connects x to the origin. Then the plane through the origin x and orthogonal to the vector nu splits, in view of the symmetry, splits omega star in two parts with equal volume. So again, we can perform the symmetrization. One of the two new domains that we obtain is again optimal. The associated eigenfunction is the reflection of V star of one of the two pieces. So this reflection should be smooth. And since it is smooth, the derivative with respect in the direction u should be 0 because of the symmetry. So we get that this V star is for sure radial because it is analytic and the tangential derivatives are equal to 0. But also the original u is radial because u is itself an analytic function on a connected domain, which is omega. So our u, the eigenfunction of the optimal domain, is radial, enjoys some circular symmetry. Let's see that also omega has to enjoy some circular symmetry. So this is done in this way. Well, so u with respect to the new origin is a function which depends only on the distance to the origin, and it is a strictly positive function. So what one can show is that, well, first of all, there are no inner cracks, because since the function now is radial and the domain is connected, the cracks should be jump set. But now there is no jump set inside, because the trace from here, it's the same of the trace from here, because it depends only on the radius and the domain is connected. Okay? So the inner cracks disappears on an optimal domain, and then what is left is the reduced boundary. And one can check that on the reduced boundary we have a Robin boundary condition, because the function u can be seen to be smooth on an open set contained the closure of omega. So what we get is that on the essential part of the boundary we have precisely the Robin condition of the beginning. And this Robin condition entails immediately some constraint on the boundary, because in order for this equality to be satisfied, so n is the normal almost everywhere on the reduced boundary. The other terms are completely smooth. ER is the radial vector. So in order for this equality to be satisfied, for sure, the reduced boundary, the essential boundary, should belong to this region, which depends only on the eigenfunctions, on the eigenfunction C. So in a certain sense, we could say that there are regions in the space which are forbidden for the boundary, because otherwise the Robin condition is not satisfied. Now it's easy to see that omega is either a ball or an annulus. Let me show you very briefly how can we do it. There are two cases. Either the origin belongs to the closure of omega, or the origin is far from the domain. Let's pick up the first case. Well, in the first case, we have that could be, for example, the picture that 0 is a point at the boundary of our optimal domain, which for the moment has not any circular symmetry. Then it's easy to see that the function psi, which gives this radial eigenfunction, has this shape. So it's defined up to the origin, and in view of the differential equation, it should come to the origin with a 0 slope. So this means that the origin is a forbidden place for the boundary, because we have that since psi prime of 0 is equal to 0, the quotient cannot be greater than beta. So 0 is a forbidden place for the boundary, which means that 0 is inside the boundary. So is inside the domain, sorry. So this means that we have a small ball inside the domain. Then we take the ball, we enlarge the ball until we touch the boundary. Then we compare the eigenvalue of the ball with the eigenvalue of omega. We compare the eigenvalue of the ball by using this test, the eigenfunction itself. And a simple, very simple integration by parts shows that indeed the eigenvalue of the ball is better than the eigenvalue of omega, is less or equal. So this means that if the ball is not the entire omega, then the ball is set with a strictly lower volume, but with a better eigenvalue, which is impossible by rescaling, by the monotonicity under rescaling. And so in this situation, the domain should be the ball. The second situation is pretty similar. One shows that there are forbidden places for the boundary. One proves that we have an annulus inside. We let the annulus enlarge until we touch the boundary. And again, we compare the eigenvalue of the annulus with respect to the eigenvalue of omega, and we see that the eigenvalue of the annulus is better. And now, okay, now the geometry now is very simple, because the optimal domains are either ball or annuli. And then we compare directly, and we prove that indeed the domain is a ball. And since now we have the Faber-Cran inequality, it's a good place to stop. And I thank you for your attention.